This semester, I've been making 2-hour drives to campus. And quite knowingly, as estimated by researchers Thomas et al., during this 2-hour drive, I experience about 10 minutes of complete blindness to objects in my visual environment. Don't believe me? Let me convince you. Theorizing the antithetical, motion-induced blindness in a static image, and its interaction with optic flow. Hi, I'm Vishnu, and I'm here to tell you a bit about the research that we've been doing at the Sensation and Perception Lab at UNH Manchester. Well, virtually, of course. Oh, cut! Okay. Anyways, here we go. Motion-induced blindness is the name of the game, and its study was first made popular by Bonnet and colleagues in a format that looks similar to what you see right now. Let me demonstrate. Stare at the fixation point in the center and be mindful of the yellow dots in the corners. They should blink in and out of consciousness without your control. And I promise there's no manipulations here, and the effect, as you'll see, will kick in the first few seconds. So again, stare at the fixation point and be mindful of the yellow dots disappearing in and out. So I hope you're able to experience the mysterious effect that is motion-induced blindness, with the yellow dot blinking out of your consciousness, out of your control. And so my research project this semester has developed from some variations to what we consider the traditional form of motion-induced blindness that I just introduced you to. And it's based on some core concepts, 3 of them, that I wanted to introduce to you first. This is the truly antithetical aspect of this project. So earlier last year, we got a little serious about a shy little anomaly to motion-induced blindness, or MIB from now on. We observed that MIB stimuli, even without the motion, although much less effectively, were able to induce target disappearance similar to that of a moving MIB stimulus. So in other words, this was motion-induced blindness, but without the motion. And the reason I think these 2 phenomena are related is because the disappearance in terms of the experience of the observer is very, very similar. And so but to my dismay, static conditions are, however, often used as control conditions in many studies, just like Thomas et al. Did right here. Note here that none of the static conditions indicated here on the graphs have a disappearance of 0. And in some cases, such as the one on the top right, you can even see that it's fairly high and comparable to other conditions. And to further support this point, past studies from our own lab have also indicated that static disappearance, indicated here as condition 7, just isn't 0. It always has some amount of disappearance occurring. That said, the question motivating this aspect of the study is, if the phenomenon of motion-induced blindness, by definition, involves disappearance in the foreground target in the presence of a moving background, then why is it that there's any disappearance in the absolute absence of moving background? So to characterize this relationship between motion-induced blindness conditions and their static counterparts, all of the conditions in this study, a total of 4 of them, were given a corresponding static condition, which was basically just a snapshot of that trial and at a random point in its 30-second length. There was also an interesting static image that just came to mind this semester, for which our lab group observed a disappearance very similar to MIB. And we were left quite speechless as to why it worked, as you can see right here. So we thought, let's get some data and see how it goes from there. I must say, however, as a preview probably for Winter Symposium in the fall, we also did some experimentation with Gestalt psychology in one other study this semester. And I'm having a hunch that the way things have been working for this condition with all these rays, it could probably be explained by Gestalt psychology. We'll see. MIB largely exists as a laboratory phenomenon that is rarely observed or applied to the real world. But it is arguable that we simply don't notice it because it involves disappearance of objects that are largely in our peripheral visual areas that are often out of our attentional interest, if I may. So that being addressed, what you saw in the beginning of this video, that was a mild exaggeration. But there is a burning need to find an area of life where there's a moving background and an immotile foreground so that we can observe MIB. And driving makes for one of the most common scenarios where the pattern of the background's movement can be characterized by the term optic flow. So now, let's head back out to the car.
Alright, so here's a video of me driving on the highway. Somewhere in the center of the screen, you'll notice a billboard that I've highlighted. Notice its trajectory. And similarly, of all objects starting in the center of the screen, just notice where they go. And here we go.
In the series, the character who's based on you, his name is
And
Wesley,
right there.
makes a daring escape from Brooklyn, the Williamsburg area of Brooklyn, to Berlin, where her mother lives. That's really not your story. You went from Brooklyn to...
So, you see how points were moving from the center out to your periphery? Very much like this. So, I think you get the point. With this entire explanation about the relation between how things look when you're driving and optic flow, you can understand what Thomas et al. Researchers had in mind as they compared a regular MIB condition with, as we say in technical jargon, zero coherence. That is when the dots in the background, which represent the moving background, move in a very random pattern. When they compared that regular traditional MIB stimulus to an optic flow motion-induced blindness stimulus, they were able to indicate, get this, that optic flow condition had the same disappearing effectiveness as a regular MIB stimulus. If you're thinking what I'm thinking, we can now say that MIB might really happen in real life. And Thomas et al.'s main suggestion for further research, therefore, was to test whether these results, where optic flow condition and MIB condition are, have the same effectiveness, whether that could be replicated in a real-world scenario, heavily suggesting that driving would be the best candidate for this test. And guess what? That's what we did. Finally, a third parameter of interest is drawn from Seherai and colleagues, who had demonstrated that by increasing visual stimulation in the MIB stimulus, or in other words, attentional load, they could induce or exacerbate target disappearance. It's otherwise also reported by Bonnet et al. That when stimulated with faster background speeds or more high contrast elements in the background, target disappearance could be exaggerated. So this experiment wanted to, in conjunction with the other factors that I've been talking about, see if these results could be replicated. Alright, so finally we get to talk about what I did for this experiment. So there's a total of 9 conditions, and we used them to respond to the concepts that I just talked about. And you can see them right here. So first one that we have is our regular MIB stimulus, zero coherence. So the dots on the background are just moving randomly. It's our control condition in a way. Then we have our regular MIB stimulus, but its static version, also a sort of control here. Then we have, in response to Thomas et al., like what they had wished for, we have a driving condition. Right after that, we also have its static version. Then we have a driving rain condition. What's that? So the rain on a windshield is predicted here to act as additional attentional load. That's quite how it looks like if you look at the trials. And so it's predicted here that we are increasing attentional load for the driving rain condition, and that should probably exacerbate disappearance. And so there's also a static version of that, of course. And then finally we have a optic flow laboratory version. So it's optic flow, but just dots moving in that pattern instead of, a video of driving. And then there's a static picture of that, of course. And finally, we have that weird static phenomenon of the rays thing that I showed you before. So for every single condition, there's 3 trials. Each trial lasts 30 seconds. And so I basically made one 20-minute-ish video that played all of these trials in succession and in a random order. The order, although, was same for all participants, although random. So for data analysis, for each trial, for every subject, I took the mean to get a mean score for duration of disappearance of a target within a trial, and the frequency of disappearance as well. So then for every subject, this compiled data was further compiled in that I took the mean for every single condition throughout all subjects, and then I also took the median for both duration and frequency. That's that, and now here comes tonight's main event. I'm thinking about how to make this feel like more of a climax. It's the results section after all. Oh, let me just poke on the prefrontal cortex of my little voodoo brain doll that I have here. You're not supposed to poke too hard, of course, otherwise it damages your brain tissue. It's just a little Eureka! just before we move on to the graphs, one tiny note. I've included both mean and median values for all of our conditions in the graph, and I've done so for a few reasons. The median has a great benefit over the mean in that it kind of discounts outlier values, and in the case of motion-induced blindness, this is really helpful, especially because here our sample size is quite small, and again with motion-induced blindness, there's a lot of individual variability in that people have at times like really different amounts of disappearance, although they follow the same trend, but have a really huge difference in the amount of disappearance that they report. And for that reason, using medians at times is better for visualizing trends. Of course, when we say that we're using mean and medians interchangeably, that means that we won't have the privilege of drawing some hard conclusions, but that, and as such, wasn't the purpose of the study, as this is a pilot study. And the purpose here is to visualize trends and be able to make good decisions for future research based on this one. All right, moving on to the graphs.
Alrighty, let me introduce you to my lovely graphs over here. The x-axis represents all of our conditions, all 9 of them, and the y-axis represents, well, different things for different bars. The dark blue bar represents the mean duration of disappearance in seconds for every single condition. The median duration of disappearance in seconds is represented by the light blue bar. And the frequency, this is the mean frequency, and which essentially is the amount of times that disappearance occurs within a trial for a condition. And that's represented by our red bars, and since it's a mean, that's why this is in decimals right now. So some very clear trends, of course. Motion-induced blindness was the leader here in terms of disappearance and frequency, but very closely followed by optic flow, and then by the driving rain condition, and then by the driving condition. The trends here you can see are more apparent when you look at the median values. Also to note, the static conditions were pretty identical. Very interesting, very intriguing. Lots of implications. And then the final raise condition, the weird one, that had a median of 0, first of all, and the mean was 3.7 and a low frequency of 0.7. Interesting. A lot to unpack here. Moving on.
Okay, so let's draw some inferences. First off, Thomas et al.'s results were replicated. We can see that the optic flow laboratory condition did have just as much as effectiveness in terms of duration and frequency as the regular MIB condition. Second, although the effect is weaker than the optic flow laboratory condition, the data does suggest that there's considerable likelihood that MIB occurs during driving. And I would say that it's exacerbated when your windshield is dirty or wet by rain. And this touches into the attentional load aspect. So although the difference might not seem too apparent, over here is the place that I would say look at the median. The results, whether they are statistically significant or not, we do not know. So can't draw a conclusion here, but definitely an interesting trend. Thirdly, I wanted to talk about a few next steps here. First off, it would be interesting to talk about the role of auditory and tactile distractors instead of visual distractors, like the rain in this case, and see their effects on changing the effectiveness of motion-induced blindness. This would have some really interesting inferences for association areas in the brain, which are places where sensory information from different pathways come together. Secondly, I would also want to look into the aspect of phone usage. That would be a little bit different from the rain condition as a visual distractor. I think it would apply the combination of motion-induced blindness with change blindness. I don't want to go into too much detail over there, but I would encourage to look at the other studies done in our lab, since one of our student experimenters has done a study on change blindness. Next, let's see, what do we have? Oh yeah, wait, we need better experimentation. Oh man, we were all doing our experiments at our own homes, and so there's a lot of uncontrolled variables here. But as I mentioned, the data is really solid, nevertheless. But we don't have any error bars, so we don't know statistical significance. But the data still is pretty. So yeah, some better experimentation will really help validate the results that we have. Coming to the static conditions, as you saw, they did not follow the trends of the motile counterparts. And this would be some evidence to suggest that the static condition, the static disappearance, is just different from motion-induced blindness, and perhaps they just happen to bump into each other in our stimuli. And yeah, that would be my inference here. It's evidence for me to suggest that static blindness, if it's a new thing now, operates on a different mechanism than motion-induced blindness per this data. And yes, the raise condition, we saw that there was a huge discrepancy between the mean and the median, and I would attribute this to issues and discrepancies in experimental protocol. I know, experimenter bias, but that's what I would like to think it is, and I don't think it's enough evidence to suggest that this is a field which shouldn't be touched upon in further research. I definitely think that with more control we would have some more effects, especially because when I did it as a subject, I know that it worked for me very strongly. That's probably why the mean was all the way up. That finishes my inferences here. I would love to hear your participation in terms of your own inferences that I didn't notice. Any questions, any comments? I would love that. Thank you very much for viewing this presentation. I find it important to end this video by extending a special thanks to the following people without whom this project would sincerely not be possible. Dr. Sparrow is my faculty advisor, and he has extensively helped me plan this project. He also taught me how to use Psykinematics, the software we use for designing this experiment. Robbie Scaff is a dear friend who taught me how to use DaVinci Resolve, the software I use for making this video and my compiled trial video for my experiment. Our lab team this semester consisted of Alina, Holly, Michaela, and Helen, and they have been wonderful people to have insightful academic conversations with. Thank you, everyone. Now, if you're still watching this video, even after my thank yous, and you didn't end the video right with the sign that said thank you, I think it means that you're interested in the content of this video. And in that case, dear motion-induced blindness enthusiast, I have a thing for you. If you've seen Guardians of the Galaxy, there's a scene where Drax is standing and eating chips, but so slow, and he claims that he's invisible because of that. Because he's so slow that he's practically not moving, he's static, he becomes invisible. Static blindness much, eh? Alright, thank you very much for watching. This has been great.